Hello, thank you for joining us today. My name is Hanan Moller. I'm a customer solutions architect and the director of the application engineering group at ULTRASoC. In our talk today, we look at some of the problems faced in designing modern systems, in particular heterogeneous ones. I will give you a brief overview of the ULTRASoC embedded analytics architecture. Then we will look at a typical modern SoC architecture. Finally, dive into some specific example of how such a device really needs a more up-to-date and modern approach to development, bring up, debug, and even in-life analysis in the field. So it's not about the ISA and it's not about the core. To me, computers' problem is largely solved. This may come across as heresy, but the objective is to get the product out there in time and cost effectively. And that means to me that the challenge is all about systemic complexity. This comes from things such as ad hoc programming paradigms. This means where a system has not been designed with a particular programming paradigm in mind, and so you have a collection of different programming methodologies to get your system up and running. There's processor-to-processor interactions. This comes from multi-core and many-core heterogeneous systems with varying degrees of coherency requirements. Hardware-to-software interactions. This is talking to hardware accelerators, for example. The interconnects, behavior of those interconnects. Systems are not formally architected. Yes, we start off having a nice clean architecture, but then over time we find out that things get bolted on and all this nice clean design disappears. With all of that in mind, you also end up having unknown workloads and massive amounts of data that you had not predicted before. The end result is that traditional paradigms for development and particular debug do not work anymore. Let us now take a tour of the portfolio of IP provided by ULTRASoC. This IP is integrated into your SoC to build your embedded analytics solution. Here is a very high-level view of your SoC. It may contain multiple processors from different vendors with different ISAs, ARM, RISC-V, just to name a few. Some DSPs, some custom logic blocks, maybe an accelerator for a specific function, memory controllers, interface controllers, and so on. There will be some interconnect, whether a flat or hierarchical or some sort of a NOC, providing the required connectivity within the system. The first group of IPs are the ULTRASoC analytic modules. These modules monitor and in some cases interact with different parts of the SoC. Let's look at the monitors first. On the left here, we have the bus monitor. The bus monitor supporting interfaces such as AXI, ACE, and CHI is a protocol and transaction-aware IP. At runtime, you can program the bus monitor to filter for specific transactions. For example, you may want to look at transactions that are targeting a particular memory range, address range, or transactions that come from a particular source in the system. And this allows you to focus just on transactions that you care about rather than have a lot of data of everything that is happening on the interface. On top of filtering capabilities that we just talked about, the bus monitor has an extensive set of counters that can count different metrics on the interface. So for example, you can count transactions by type, whether this is snoop transactions, read transactions, write transactions, measure latencies, minimum latencies, maximum latencies of transactions, and so on. The bus monitor can also collect trace from the interfaces. So you might have a scenario whereby you want to see the specific set of transactions which are issued, let's say, from a particular source in the system to a particular destination in the system, and have a timed view of those transactions and their content. The next monitor we want to talk about is the status monitor. Think of the status monitor as an on-chip logic analyzer. You may have some custom logic where you need to observe particular internal signals and characterize the behavior and performance of this IP. You will instantiate a status monitor to observe those signals, and then when you're running the system, you can configure the status monitor to perform actions such as, for example, measuring the time between two specific occurrences of a signal on that interface. Like the bus monitor, the status monitor is able to count events, measure latencies, and collect trace on the relevant signals to which it is connected. The PAM, or Processor Analytic Modules, provide connectivity between ULTRASoC IP and the debug module interfaces of specific processors. The PAMs support interfaces such as JTAG, APB, and AXI. Those are used in cases of processor debug and run control. When it comes to processor trace or instruction trace, we have a number of IPs that support that, whether for traditional trace from processors such as ARM, we can use a trace receiver, or we have the trace encoder, which works with the RISC-V processor trace interface to create a compressed trace information. All of those analytic modules need to be configured, and the data collected by them needs to be sent to analysis. And this is done by our message fabric. The message fabric is built using our message engine, which provides connectivity and data transfer capabilities, as well as very extensive and flexible cross-triggering capabilities. It is important to note that this message fabric is dedicated for ULTRASoC functionality, and as such does not use the SoC's normal or functional interconnect for analytics purposes. The communicators provide the gateway between the hardware and the software control plane. The software control plane might be running off-chip, in which case we will use things like a JTAG or USB 2 or EBC plus USB 3 communication. And in cases of on-chip analytics, we can use the AXI communicator or the analysis subsystem that is shown here on the bottom right. The active managers provide solutions for security and safety requirements. The lockstep manager provides a lockstep solution for 2 or more processors for safety purposes, whereas the bus sentry provides security on specific interfaces by observing each and every transaction running on the interface and checking for whether or not the transaction is allowed to go through. Last but not least, there are some security concerns around using the ULTRASoC IP, which provides a lot of visibility into the system, and the ULTRASoC IP all have the ability to lock specific interfaces such that unauthorized users will not have access to some or all of the ULTRASoC IP. So here we have an example of a typical modern SoC. It includes some machine learning site capabilities in the form of vector processing subsystem, as well as accelerators. Let's now look at some issues that our customers have experienced in the past. We will go through some examples shortly, and those will help identify some of these problems and point to some solutions. Consider caches, for example. Caches have some advantages, but they do have some disadvantages, especially in a real-time embedded system. Scheduling of tasks and workloads within the multi-core environment can be very challenging. We're not talking about operating system level scheduling, but rather scheduling of tasks between different cores and multiple accelerators, all the while having to coordinate access to various stored resources, in particular memory. Deadlock or system hanging is another very common example that our customers have experienced. Where do the MIPS go, or why is the CPU not performing as expected? Understanding the root cause for this is key to getting the product out on time and to performance levels needed. The behavior of your NOC. Is the NOC oversubscribed or maybe unbalanced? All of those issues feed into the final product, both in terms of delivery timelines, but also how well it will perform. Let us now look at some examples and usage scenarios of ULTRASoC technology that can help identify and solve some of these problems. So how does ULTRASoC help? Well, let's take the SoC that we have just looked at. What I've done here is instrumented that system with some ULTRASoC IP, analytic modules, active managers, and communicators. These ULTRASoC IPs are shown here in this exciting gray color. We have a whole collection of monitors or introspection probes, and I'm just showing a small handful of them. As I said earlier, the NOC bus monitor and the AXI bus monitor are protocol-aware transaction monitors. This means that they understand the underlying protocol of the interface they are observing. They also track the outstanding transactions in flight. The monitors themselves are runtime programmable, meaning that at runtime we can get those modules to look for certain transactions, report on certain transactions, and collect performance metrics such as latency, counts, measure min, max, average values, and so on. The monitor can also capture or trace the transactions that they are observing. This trace information can be stored locally within the monitors before being collected for analysis. Within the NOC itself, we place some simpler NOC monitors. These are not necessarily trackers. They do not track individual transactions in flight, but you can program them at runtime to look at different kinds of transactions and provide information that they are observing. We also have a status monitor IP. In this case, it is connected to the system of accelerators. The status monitor does not know what it's connected to, so at runtime, you program the status monitor to understand the meaning of the signals it is seeing and what to do when certain conditions are met. Status monitor can also perform actions such as counting and providing different kinds of metrics, as well as capturing trace. The data from these monitors ends up going into the ULTRASoC message passing fabric, which we described earlier. We're not showing this message fabric in here because it would make the diagram even busier than it already is. And then ultimately, all the data is transported to some sort of communicator, and that communicator could take the data that's generated either off-chip or to something on-chip. In this example, we have an EBC connected to USB 3 controller. The EBC is the external buffer communicator, which provides a way of talking USB 3 protocol off-chip. In the next few minutes, we will go through some examples of how we use these ULTRASoC modules to provide visibility and information on system behavior. In this example, we're going to look for system hang or deadlock. We do this by configuring the NOC bus monitor to look at transactions going by from the vector engine to the NOC. We configure the NOC monitor to take a copy of the transactions, put them in a circular buffer inside the monitor, and look for transactions whose response takes more than a certain amount of time. That time in itself is configurable at runtime. When the NOC monitor detects this condition, that is, the response takes more than this configured amount of time, then those transactions that led up to the hang or that deadlock are already in a circular buffer within the NOC bus monitor itself. Now those transactions can either be pushed out or pulled out via some software entity, either off-chip or on-chip for further analysis. In this example, we're looking at the activity of one of the bare metal CPUs. Here we're taking an AXI bus monitor and looking at the iCache port, counting the number of transactions seen by that bus monitor in a window of time. When that window of time expires, the count that the bus monitor itself generates is sent across the message passing fabric I mentioned earlier, then out through the EBC, which then goes out through the USB controller. In this case, it is USB 3. By taking those counts, we can build a pie chart such as the one you see here on the top left. And this pie chart shows us that 8% of the time the branch predictor is mispredicting, while 12% of the time we're just suffering from misplacement of code. With armed with this information, we can go to our compiler writers and software engineers to write better hints to the branch predictor to potentially and hopefully eliminate this 8%. We can also get the bus monitor to do min-max average of the cache miss duration. Whilst the average might be fine, it is the maximum latency that you experience which will have a knock-on effect on the amount of work that the CPU will do. We can also get the data that this bus monitor generates and produce a histogram which shows the profile of all transactions seen over time. In this example, we're observing traffic coming out of the 2 vector processors and one of the scalar processors in the OS subsystem. Remember, the scalar processor over here is the one that's doing the orchestration of work between various system components. By configuring the NOC bus monitors to observe Snoop traffic as well as data cache traffic to and from these processors, we can plot charts such as the one seen here on the left-hand side with the data collected by those monitors. What these graphs can tell us in here is that some of the behavior around CPU number 1 is a bit anomalous. It is getting a lot of snoops from CPU 0. All this extra NOC traffic increases the cache latency and reduces the performance for CPU number 1. What that means is that it would be useful for the software system architect to review how code partitioning is happening in the system and improve it to increase and enhance the throughput of the system. In this example, we are configuring the NOC bus monitors to look at link credits and link activity. Within the NOC itself, we have those much simpler NOC monitors that are observing the credits inside the NOC. We're looking at various different kinds of credits inside the NOC, in this particular example, per channel credits. By looking at this collected data, we can see that at this NOC monitor point over here, we have a poor supply of Snoop credits and write data channel credits. This could suggest that the CPU at that particular point is the target of more Snoops than it can handle. However, looking at the bottom graph at link activity, we can see that the write data channel is heavily loaded within the system, which may explain the behavior relating to the poor supply of write data credits. In this example, we are observing the execution of one of the vector engines. We have configured the processor trace encoder to be in cycle accurate mode, observing the execution of a particular function or when the CPU executes from a particular memory location. The packets of information that this trace encoder generates will be transported onto the message passing fabric, which then will forward them to the EBC, which that means that the USB 3 controller will send them out via the USB 3 PHY. At the same time, we have a status monitor looking at activity within the accelerators. What we have in here, in this particular case, is the status monitor looking at when a particular accelerator starts working and when it finishes its work. From that data that the status monitor generates, in effect, it gives us a start-finish time for each of the accelerator activity units or workloads. We can plot a chart like the one shown here at the bottom. We can see that most of the time, all the accelerators seem to be doing roughly about the same amount of work, except the case for accelerator number 1 here, where the penultimate workload takes a much longer time. And the consequence of that is that the execution of the instruction in the vector engine has stalled waiting for work to finish in the accelerator. We can see that in the decoded information that the debugger is displaying in the upper text window, where this particular instruction took a really long number of clock cycles. So hopefully the example I just showed you give you a good idea of the capabilities of the ULTRASoC embedded analytics architecture. In summary, the challenge today is systemic complexity. This complexity arises from processor-to-processor interactions, hardware-software interactions, the performance and capabilities of a NOC, and so on. All this complexity translates to dollars. The long-tail problem will impact performance, which means that average performance is not an appropriate measure of what's acceptable. And having profilers that affect the behavior of the system is not acceptable either. So what ULTRASoC does is provide a system-wide, non-intrusive wire speed monitoring system. You can actually have something on chip that takes that data and provides analytics and use data science and ML to help the engineers identify problems. What we think of as a 21st century solution. Thank you very much for listening.